Amides are the least reactive derivative of carboxylic acid. They only undergo two types of reactions: reduction and hydrolysis. Let's start with the hydrolysis. Hydrolysis of amide can be in presence of an acidic or a basic medium. If you hydrolyze amide in presence of an acidic medium, then your product is going to be a carboxylic acid. Always, whenever you are adding water to the derivative of the carboxylic acid, your product will be a carboxylic acid. However, you need to follow the medium that you are working with. So, if your medium is acidic, then your product is going to be an acid. If your medium is basic, then your product is going to be the base of the acid. So what we're targeting in these types of reactions is the amide bond. Notice here that nitrogen is the one that is leaving. However, we have rules for nitrogen like we did for oxygen. Remember, when we were talking about oxygen, we said that oxygen leaves whenever you have a basic medium in a form of a lone pair, and if you have an acidic medium, it leaves in a form of a positive charge. This is exactly the same here with nitrogen. So nitrogen, whenever you have a basic medium, it's going to leave in a form of a lone pair. And if you have an acidic medium, it should leave in a form of a positive charge. In your product, in your organic product, you have no trace of nitrogen. So what you're doing here is you're breaking that amide bond and the nitrogen leaves. So in order to leave, it needs to follow the medium that you are working with. Let's consider the first case, which is the mechanism in acidic medium. So as usual, acidic medium, you are starting to protonate the oxygen to make this carbon an electrophilic carbon. So once the carbon over here becomes electrophilic after the protonation, now your nucleophile is going to attack. Your nucleophile is going to be the water, okay? So that water now is going to attack, form a lone pair on the oxygen. With these types of reactions, we want to avoid adding too much of reagents. So if you have an extra hydrogen and you want to get rid of that, look at your compound and see if there is any base in your compound that is available to pick that hydrogen. So you can do a proton transfer. So when the water attacks, you're going to end up having an extra hydrogen on the oxygen. Now, our target, notice here that our target is to break the amide bond and to allow this to leave. However, for the nitrogen to leave, we want to reach the nitrogen having a positive charge. And for the nitrogen to have a positive charge, it needs to have 4 bonds around it. Right now, it has 3 bonds around it. So I just want to introduce a hydrogen in there so that the nitrogen is a positive charge and then it can leave in the acidic medium. So I need to protonate the nitrogen somehow by doing a hydrogen shift or a proton transfer. So when you do this now, see, the nitrogen is now a plus charge, so now it can leave by simple resonance. So you move the lone pairs, you break the bond between the carbon and the nitrogen, and now the ammonia is going to leave. Ammonia cannot stand like this on its own in the solution because ammonia like that is a base and your medium is an acid. So any acidic hydrogen that you have in your product, this is an extra acidic hydrogen. Ammonia is going to come and pick it up so that your product is going to be an acid, and the ion that you're going to form needs to be also an acidic ion. It needs to be compatible with the medium that you are working with. Now, when we're working with a basic medium, you don't do any protonation in the first step. The nucleophile immediately attacks, form a negative charge on the oxygen. Now, our target in the basic medium is to break the amide bond and allow the nitrogen to leave in a form of a lone pair. So that is going to be a good leaving group. And right now it is in a form of a lone pair, so it can leave easily. So when the base attacks forms a negative charge, by a simple resonance, you can break the bond and the nitrogen can leave. When the nitrogen leaves, it's going to be basic. You already have an acid in your product, so that base is going to pick the acid in there, the acidic hydrogen, and become a weaker base in this case. So these two are bases, they are compatible with the medium that they are in. The second type of reaction is the reduction of amide. You are not responsible for the mechanism, but with this one, we're going to use a strong reducing agent. We're not going to use sodium borohydride because it won't have any reaction with the amides. But the lithium aluminum hydride will reduce all the types of amides, primary, secondary, or tertiary. And the reduction is going to be on the carbonyl. The nitrogen, the NH2, nothing is going to happen to it. It's going to stay. But the carbonyl is going to turn into a CH2. As I said, mechanism you're not responsible for. This is an example. No matter what type of amide you're working with, you're reducing the carbonyl into a CH2. You're not actually adding a carbon, so you're going to end up having the same number of carbons that you started with, except you are going to get rid of the double bond O and you are going to replace that with hydrogens. Nitriles, which are carbon and triple bond, and these are derivatives of carboxylic acid because we're going to use those in order to prepare carboxylic acids by hydrolysis. We went over these reactions in chapter 17. So let's start with the preparation of nitriles. This goes back to organic 1. So you can do an SN2 reaction with sodium cyanide in there. You would need, however, an sp3 hybrid carbon so that the substitution can happen. It is a one-step reaction. The Cn minus attacks. This is a strong nucleophile. The chlorine is going to leave, and you're going to end up having your cyanide. This is one way of preparing nitrile. Another way is from chapter 18, when we form the cyanohydrin from the carbonyl. So if you use sodium cyanide or potassium cyanide, or if you use HCN. So this is going to be in a basic medium, or you can use the HCN. This is a reaction that we also talked about in acidic medium. Whether you use this or that, the mechanism is going to differ, but the product is going to be the same, which is going to be the cyanohydrin. The Cn minus in the basic medium is going to attack the carbonyl, form a negative charge that gets protonated. If you're working with an acidic medium, the first step, you are going to protonate the oxygen, and then the Cn minus is going to attack, and you're still going to get the cyanohydrin. The whole idea here is to introduce the cyanide that we can later react and hydrolyze in order to get to the carboxylic acid. You can also form the cyanide. This is a new way. You can also form the cyanide by losing water from the amide. So you start with the amide and use a dehydrating agent. The dehydrating agents here are a couple of them. So all of those in there, pick one. And the dehydrating agent will allow the amide to lose water. You're going to lose 2 hydrogens from the nitrogen and then oxygen from the carbon. And you're going to form a triple bond between the carbon and the nitrogen. Again, we are not adding any carbons in here. We're just removing the water. There are 2 reactions of the nitriles that you are going to be responsible for. The first one is the hydrolysis. We brushed on this in chapter 17. We're going to consider its detailed mechanism. So we said that nitriles, these are derivatives of carboxylic acid because we're going to use them in order to make carboxylic acids. So to prepare carboxylic acids from nitriles, you simply do hydrolysis. And the hydrolysis can be either in acidic medium or it can be in basic medium. I am not adding any carbons in here. So this carbon stays. All I am doing in the acidic medium is that I am adding hydrogens to the nitrogen to make it a positive charge so that it can leave. and I will end up getting a carboxylic acid. And for the basic medium, I'm still adding hydrogens to the nitrogen to make it a lone pair so that it can leave, and I will end up getting my base of the acid. In either one of those, you are prepping the carboxylic acid because in the basic medium, I can go a step further and add an additional acid in there, and I will end up getting my carboxylic acid. So let's go into chapter 17 notes in order to look at the mechanism of the hydrolysis of cyanide in basic and acidic medium. So in basic medium, you're using an OH in there. And again, our target is to add hydrogens to the nitrogen and make it leave in a form of NH2. When you're looking at carbon triple bond nitrogen, this is going to behave exactly like a carbon double bond out because the oxygen and the nitrogen, these are electronegative elements. So as the carbon here is partial positive, this is the same thing. The carbon next to the nitrogen is going to be an electrophile because the nitrogen is more electronegative, so it's going to pull electrons towards itself, making this carbon an electrophilic carbon. So we're going to start by adding the nucleophile to the partial positive charge carbon. Every time we make a bond, we're going to break a bond. We're going to end up having a negative charge on the nitrogen. So this is our chance now to use the water as a solvent. So here the water acts as a solvent. And the role of the solvent is to give hydrogens. This is the role of the solvent. So the lone pairs of the nitrogen now are going to act as a base. They're going to take a hydrogen from the water solvent, and this is going to be my first hydrogen in there. So remember our target here. Our target is to change the nitrogen into a lone pair. So to have a lone pair with a zero charge, it needs to have 3 bonds in there. So it needs to have 2 hydrogens next to it together with whatever R group it's connected to. Right now I have 1 hydrogen. I want to introduce the second one. So now I have a base and an acid in the same molecule. I can do a proton transfer. So when you do a proton transfer in there, you're going to now reach a point where you have a nitrogen with 2 hydrogens, but still you have a double bond. You want to get rid of the double bond before you allow this leaving group to leave here. So by a simple resonance, I'm going to introduce a lone pair to the nitrogen, and I'm going to end up getting my intermediate. So this one over here is going to be the intermediate in the reaction. In our case here, this is a primary amide. Now, this primary amide cannot be isolated. You cannot stop this reaction here. This reaction is going to continue now. So now I'm going to use another mole of that base, which is a nucleophile. And that nucleophile, because see that second mole that I am adding of the OH, this is the one that is going to give me the OH of the acid. So that OH is going to add now to the carbonyl, form a negative charge, and now the negative charge is going to close and the NH2 is going to leave. This now is a good leaving group. Make your acid, your medium is basic, the base is going to come pick the hydrogen and you're going to get the conjugate base. In acidic medium, I'm going to change the nitrogen into a positive charge. So we're going to keep introducing hydrogens to it in the same way. But the difference here is that I'm doing an acidic medium rather than a basic medium. So my first step, the water cannot attack because this is a weak nucleophile. So it's not going to attack this partial positive carbon. What's going to happen is that I'm going to end up having a protonation in the first step. So I'm going to end up having a base acid reaction. In the protonation in the first step. So you protonate the nitrogen like we used to protonate the oxygen. You protonate the nitrogen. This is the first hydrogen that you introduced on the nitrogen. Now you're going to go ahead and add your nucleophile. When you add your nucleophile, you're going to add it all. See the difference between adding water as a solvent and adding water as a nucleophile. When you add water as a nucleophile, you're going to form a bond between the carbon and the oxygen and add the whole thing. You have a base acid in your same molecule, do a proton transfer in there. And here you go. So far we have two hydrogens. We still need one more. So go ahead and add another water because I need two OHs in there to make my acid. So add another water and then do a proton transfer. And you've reached your three hydrogens on the nitrogen. You can do a simple resonance and kick out the NH3. This is a base. You have an acidic medium, so it's going to pick any acid in your product, and you're going to get your acid together with the counter ion. Another reaction for nitriles is the reduction. This one you're not responsible for the mechanism, but like the derivatives of carboxylic acid and amides, nitriles also undergo reduction. And the reduction is straightforward. You're adding two hydrogens to the carbon, two hydrogens to the nitrogen. So you're moving from a triple bond to a single bond. You're not adding any carbons though. You are starting here with four carbons. You are going to end up with four carbons. Four carbons. As usual, all derivatives of carboxylic acids have no reaction with the sodium borohydride. They do have a reaction with the lithium aluminum hydride. So I'm going to add two hydrogens to this carbon, two hydrogens to this nitrogen. So my product is going to be a primary amine. Now, if you use a milder reducing agent, then in this case, you're going to end up isolating your intermediate in the reaction. When you do reduction, you're going to pass by an intermediate before you pass by your final product. The intermediate is always an aldehyde in the reduction. So if you're using a milder oxidizing agent, then you are going to isolate the aldehyde. We are not adding any carbons in there, so this carbon is this carbon over here. The triple bond is going to break since this one is a basic medium. Then the nitrogen is going to leave in a form of a lone pair. The last reaction of the nitriles is the reaction with Grignard and alkylithium. This is a basic medium, so the nitrogen is going to leave in a form of a lone pair. The carbon of the nitrile, it's going to turn into a carbonyl throughout the process. And the R group that is linked to the organometallic reagent, whether it's a Grignard or alkylithium, that is going to be the second R of the keto. So you're going to keep the R, you're going to change this carbon into a carbonyl, and then you're going to add the second R as the R of the ketone. You are not responsible for the mechanism. So we're going to keep the benzene. We're going to change this carbon into a carbonyl. And we are going to add the R of the Grignard to the carbon of the carbonyl to make a ketone, which is the reaction. So besides forming esters from Fischer esterification, which is the reaction of the acid and the alcohol in acidic medium, we can form esters by a reaction called Baeyer-Villiger reaction. Now, this reaction uses a peroxy acid. A peroxy acid is an acid that has two oxygens that are connected with a sigma bond. This is called a peroxy or a peroxide, connected with a bond. So you can vary the R. So this is an R, and we can vary the R. We can have an R as a phenyl. We can have an R as a CH3. We can have our R group to be a benzene. If we have a chlorine on the meta position and then the peroxy acid, then this is going to be called a meta-chloroperoxy benzoic acid. This is MCPBA that we've talked about in Organic 1. Just as a revision, what MCPBA does, if you have an alkene and you react the alkene with the MCPBA. So let's go ahead and draw its structure in there, because here it's the same concept. This is the metachloroperoxybenzoic acid, and it's a peroxy because of the two oxygens that are connected with each other. So the whole idea here is that the oxygen that is connected to the hydrogen, so this oxygen over here, it's going to come and insert itself between the carbons of the double bond. So your product for this reaction, so this reaction over here, your product is going to end up being an epoxide. Okay, so we've talked about this before. This is exactly the same thing. Every time you are using a peroxy acid, it's this oxygen that is connected to the hydrogen. This is the reactive oxygen. So it's this oxygen that you are going to insert. If you start with a ketone, the oxygen is going to get inserted between the carbonyl and the most substituted carbon. So notice here I have two sides. I have this side next to the carbonyl, and I have this carbon side next to the carbonyl. You go and you target the most substituted side, and the oxygen is going to go over here. So all what you did is you increased the number of members in the ring by 1 when you introduced the oxygen, and you formed a cyclic ester. Cyclic esters. Same thing over here. This is a most substituted side, so you look at the carbonyl and the adjacent carbon, and it's here that you insert the oxygen. The last reaction, we can prepare esters by reacting diazomethane. So this one is called a diazomethane. And diazomethane has one of these Lewis structures in there. So this is going to act as a base. If you write the Lewis structure for it, you're going to see that the carbon is going to assume a negative charge, so it's considered to be a carb anion. So that is going to act as a base. So this base is going to come, take that acidic hydrogen and form a negative charge. So when it does, you are going to end up having a CH3 in there. So when it does that, you are going to get the conjugate base in here. That is going to act as a nucleophile. It's going to attack the CH3 now that gained the hydrogen, and the nitrogen is a good leaving group, so you can make your ester. The mechanism you are not responsible for this reaction, but you are responsible for the reaction itself. And for this reaction, all what you are doing is that you are replacing the hydrogen of the acid with a CH3.